That's a great intro, and so can everybody see this okay? Maybe I should do a sound check. Can you hear that?
Yeah, sounds great.
Okay, great. Move on. All right, so that's a great setup for what I want to talk about. So I'm going to do a couple things. One, I'm just going to give some background on the kind of work that we've been doing over the past decade or so on sound synthesis for different types of physical models, and then talk about how to go from all these different phenomena-specific models and real-time models to general purpose rendering. And then I'm going to come back at the end and talk about ClinePat, which is a new fast acoustic transfer solver that we just published last year. And so the motivations for this are, I think you've seen a lot of uses for simulation of graphics for vision applications, for training data and differentiable rendering, et cetera. And so being able to do the complete picture with audiovisual simulation will then allow you to understand, how sounds come about. You don't have to worry about separating them because they're already separated. You can figure out where they arose and what the directional fields of sound transport are for all kinds of other purposes. And so, sound is really interesting too in terms of motion because it essentially tells you where the discontinuities are. It essentially tells you when the accelerations on the system change. So essentially that's the jerk that you're hearing in the system. And so it's really a rich source of information about how things change. So I want to thank all of my students and then just go on into it. So in graphics, people, simulate stuff and make pictures. They use physics because it's hard to fake it by hand. But the sound was always an afterthought. It's always something that, was added at the end, similar to what they did with old, talkies and stuff before that. In graphics, it's always some post-production, and they have all the time in the world in movies, which is essentially a 20th century art form. So if we want to be able to take any visual content and compute the sound for it, I mean, you could just do it from the image, but you could also, since we have all the geometry in graphics, just compute it from first principles. And that's the approach that I'm going to talk about today. So essentially, there's some disturbance, there's vibrations or other accelerations on the surface. These surface accelerations produce sound waves. And if we model that process literally and then try to speed it up, then we can capture all of the sound field. So we basically want to know what the radiation field is and then be able to evaluate it for your listening position, for your specific microphone or what have you, or head. And so we explored this over, for like 20 years now, and see, these are some older works. So the basic problems are there's a lot of different types of phenomena that produce sound. So there's physical complexity, and then there's the algorithmic side to it. How do you do this in the computer fast? And there's all of these wonderful algorithms and things like that. And then there's specific implementation used for different applications. If you want real time, we pre-compute things. If you want to do it offline and high quality, you have different things that you can do. And then you have to validate things to make sure that it's not garbage. So the simplest and popular type of model is just a rigid body model. And one reason is that it can be very fast. So you essentially take a solid model, a finite element model, compute its vibration modes, which are the eigenvectors, and then the frequencies are the eigenvalues. And this tells you how a stiff system vibrates. And at runtime, you can render these vibrations quickly, but you don't hear vibrations, you hear pressure waves in the air. And so for every vibration mode, you can compute an acoustic transfer field to get a sound of what the object sounds like in isolation. And this is a good starting point for making sound, but it doesn't include a lot of other things, interactions between objects and so on. But it's a very fast model that can faithfully reproduce the sound of an object in isolation, which is a starting point. So to render this at runtime, what you do is you just take the amplitude of every individual oscillator and then just multiply it by the transfer function at your listening position. This can be done extremely fast in real time. You pre-compute all the vibration modes with an eigenvalue solve. You pre-compute the transfer functions for every mode using a Helmholtz radiation solve, frequency domain wave equation. And then at runtime for your listening position X, you evaluate the mode's pressure amplitude and also the oscillator amplitude Q of T, and then sum those over all the things because of linearity of the wave equation. So that's the basic idea. It's a simplified model, but it's already got a lot of stuff that you have to do. So here's an example of just a plate. So this is just the sound model of the plate. There's no ground reflections, there's no chattering, there's no other weird coupling. This is just the simplified model. And then we explored this in a bunch of contexts. So for nonlinear vibrations, in this case, the modes couple and you get noise, which is essentially chaos. And if you have fracture, you get many little rigid bodies. So there's a system for figuring out where they are, analyzing their vibrations, analyze the radiation, and then computing that for all of them, and then methods to make it faster. You also can't just consider the force exciting objects in isolation and treating them like with rigid body solvers because they couple together. If you ignore that, then the force of the objects, excite the table and the bunny, but in reality, there's vibrations that couple things like this. And so you get all these other sound contributions. It's really quite interesting. Another thing these are focused mostly on vibrations or ringing noise, which is popular for large objects, but for tiny objects, they may not be audible at the frequencies you can hear. So their major source of acceleration of the surface isn't the vibrations, but the actual rigid body motion when the frame of reference discontinuously gets accelerated. And so during those short time scales, you get clicks. And this is really important for adding other realisms. So every sound that you hear for impact is a source of two objects, which is also an interesting separation problem. But if you just throw dice on the table and only model the table, you get this. But in practice, you have dice too. And so considering all these different surface accelerations and different models for each of them allows you to get different sounds. This is, mostly very crisp because of these acceleration noises. You can also think of other objects like acceleration sources, like this slinky is essentially a rod where every little segment is like a little rigid body that undergoes the rapid acceleration. And the previous acceleration noise models can then be used to generate the sound of this, basically as a convolution of acceleration noise sources. So there's many different collisions that you can model and figure out all these excitations of the system of tens of thousands of sound models, and then compute a final sound like this. It all happens so quickly, but there's a lot that you can fit in between the visual frames. Another thing we looked at was measurement of sound models, but another fun project was basically going the other way, trying to hallucinate videos or motions of objects just from the sounds. And it turns out you can do some interesting things here. So what we did is we took a sound clip of a typical object, say a wrench or a bulb of garlic, and then we figured out when the event times were, how loud they were at those times, which is correlated with the impact impulse. And then we were able to search the space of all possible rigid body motions that matched those contact time scales and also had plausible physics to do essentially a graph search to find motions that produced these signatures. And these are automatically hallucinated results. So I'll just stop it there, but there's like a half an hour of footage online somewhere. We've also looked at other fluids and other systems that have rapid gas expansion. I'll give you fire, which is basically part simulation and part texture synthesis. And then we've also done a lot of work on fluids, which I don't have time to talk about, where basically the bubbles vibrate and cause the fluid to vibrate like a shape-changing loudspeaker that that radiate sound. And we've looked at a lot of different models for that. I'll visit that later. But one of the sort of summaries of a lot of this early work that we did was that it basically looked at different types of models for different types of phenomena, everything designed to efficiently render that one phenomena, but it's basically treating everything separately. And there was no real integrated way to render sounds in general. So if you wanted to come up with some scenario and render it, you know, may not work for that model, or you couldn't put water in your vibrating solid, etc. So what we really want to do is build a general rendering architecture similar to what, you know, has happened in graphics, where anything you can, you know, your eyes can see, you can render. How can we put all these different types of models together in one frame? And so we did this in a project where we built a wave solver which could handle anything you put in the boundary. It would rasterize the geometry, rasterize the acceleration conditions on whatever interfaces were there, solids or fluids, and then use acoustic shaders to communicate to the wave solver and generate a low noise simulation using a finite difference solver with embedded interfaces. And this sort of system could render, you know, whatever you put in there, say a symbol, or it could render, you know, a bowl that has reflections with the floor. So previously, we would only be able to do without coupling or scattering, but with this, we can render whatever. One problem that we're confronted with is just if you're going to time step the wave equation in a box, you're looking at, you know, teraflops of work. So how can we speed this up? We're time stepping sequentially, so the limitations for parallelism are limited, are bad. So one thing we can do is this trick for parallel and time synthesis, where we take all the boundary accelerations on all the geometry, whatever it's doing, and then time slice it so we have non-zero values in little windows. So we can think of these as frames, like in graphics rendering, and then we render the contributions of to the sound produced by these non-zero values and get new sound clips, which are then added up together. So it's basically MapReduce for sound synthesis, and allows us to do cloud-based computing of more complex scenes. So we could take a clip like this of me talking and then render the result due to different boundaries that are around me, and render this in the cloud in parallel.
A, B, C, D. A, B, C, D.
And so one other benefit is that then we don't have to make assumptions about pre-computing things. We can just render water with changing geometry and get a much more realistic sound field. So this is a fully incompressible two-phase simulation of water with air bubbles vibrating, producing surface vibrations that are then coupled to the wave simulation rendered using the previous approach. All right, so I think I'll probably stop talking about that approach at this point and switch over to the other material just to stay on track. So this last paper was work at SIGGRAPH last year, and it's basically a way to compute acoustic transfer for solid objects very fast. So this is a technique, precomputed acoustic transfer, that is basically just a simple model for sound radiation for a vibrating solid. And so it gives you directionality effects and other amplitudes that you couldn't otherwise get. So the basic idea is the solid vibrates for a given vibration mode at some frequency. You can figure out the amplitude of the radiated sound around the object. So you can think of this as just a heat map which says where the object is loud and where it's quiet. And then at runtime, when you want to say how loud is it for my listening position here, you can use the amplitude to tell you which modes are loud and which ones are quiet. And that gives you most of the character of a lot of objects that you can hit, like a wine glass or something. So the problem with this approach is that it's parallel, but it's not the right kind of algorithm really for what we need. So essentially for every vibration mode of the solid, we can figure out what its radiation field is by solving the Helmholtz wave equation once for every mode, and then evaluating that solution in some way that is useful for the renderer. And the problem with this is that it can take a lot of time to do this. Like it may take, even if it only takes 5 minutes per mode, you may have 1,000 modes. So it's a lot of work. And the basic wisdom of the numerical community is just use a fast boundary element solver. This is an optimal way to evaluate the solution to the Helmholtz equation using fast multipole, etc. The problem is these are optimal methods for a different problem. This is, you have a single radiation field you want to solve. We have like hundreds of radiation fields for one model at multiple frequencies that we all want to get. So what we developed was an algorithm that's optimal in that sense, that it can actually solve these problems together. So if we want the transfer field for a single mode, we can compute it, but we can also do this not just in the frequency domain, but in the time domain, which normally you wouldn't do because of space-time complexity versus a time-independent boundary element solver. But if we allow the boundary to oscillate at a given frequency, we can go ahead and then discretize space and compute the wave field from this using finite difference. And after the initial transient goes away, we end up with this oscillating transfer function, which gives us the amplitude field that we care about, which we can basically hear. But we can also, in the time domain, do a superposition of more than one mode. So here is two vibration modes oscillating the boundary, causing accelerations, and these produce pressure waves around the solid like this. We can even throw in 10 modes. You know, the time domain solver doesn't really care. Once you evaluate the boundary conditions, the field just does its thing, and it's the same cost. And we can compute this on the GPU, and it's very fast. So the basic idea then is to do many modes at once. And so exactly how is what our algorithm ClinePat does. So we first take all of the modes of the object. So you have 300 modes of this bunny. And it's going to split the modes into these different frequencies into what we call chords. And each one of these chords is going to be simulated on a different time domain GPU wave solve to get some sound field. And then from that sound field, we will extract transfer functions for each of the modes separately using a deconflation step. And so this is the conflate, simulate, deconflate framework that we use. So what I'm going to first do is talk about the conflation step. And so the basic idea is simple. Okay, I'm going to talk about deconflation first. So if we have a field that is a superposition of multiple harmonic fields, then you can figure out the frequencies using some frequency analysis, but we actually already know the frequencies of each of these solves. So in practice then, the pressure field at any point is going to be a superposition of some partials. After the initial transient, they're basically just sines and cosines. And so we can separate them efficiently using least squares because we know the actual frequencies of each of the modes. So assuming they're just sines, then there's some mixing coefficients that we can determine using least squares. And this can be done extremely efficiently at many points in our system. So the one thing that can happen though is that if you have two frequencies which are similar, then you have ill conditioning in your separation problem. And so, you know, how likely is this to happen? Well, all the time, because objects with symmetries are going to have degenerate eigenvalues. They'll have similar vibration frequencies because they work together as a team. And so what you need to do is keep them separated. So what we do in order to do this is figure out all the frequencies, have a separation constraint so that each chord has frequencies which are separated by some epsilon, which is chosen based on the time bandwidth product. And then in practice, then you can figure out all the frequencies, how they split into chords using a simple greedy algorithm. So if you have a separation constraint, this is basically an indifference graph that there's a greedy algorithm that allows you to color this and figure out all the chords. And so this allows us to figure out which things to simulate together so that we can separate them accurately and simulate them efficiently. So we do this on a finite difference grid on a GPU wave solver. You just basically rasterize the boundary or do something better than that. And then at every boundary condition, you sum up the different oscillations due to each of the mode's frequencies. And this is basically what you simulate in a box with an absorbing boundary condition. And then in order to build a model of the wave field, we extract the solution on some shells. And then are able to evaluate it. So there's a bunch of GPU junk, which I'm not going to talk about, but at the end of the day, you can extract an outgoing sound field on some far-field acoustic transfer maps, and we use the real-valued ones, which basically look at outgoing rays and reconstruct the solution there. So at the end of the day, you end up with these cube maps, which describe each of the modes' amplitudes in different directions. And basically, the method is really fast. So instead of like several minutes or longer per mode, we can extract almost 300 modes, radiation fields for the bunny in under a minute on a single machine with a GPU. So this is the Klein-Pat algorithm. Just to give you some results here to end on. Let me see. Okay, so we took a bunch of objects from the Thingy 10K data set and automatically meshed them, computed their modes, and then ran Klein-Pat on them. We took 800 models that totaled 68,000 vibration modes. So we computed 68,000 Helmholtz transfer functions. And it took us 2 hours on one machine to do the transfer analysis versus we estimated approximately 470 days using a boundary element solver, which we did not run in time to submit the paper, and we'll never run because it would be a waste of time because the results are essentially indistinguishable. So kind of performance we're seeing is we're seeing thousands to almost 5,000 times speed up over a multi-core boundary element solver, BEM++. So this approach is fundamentally a lot faster than doing every mode separately because we can do, you know, a constant number of solves to get hundreds or thousands of modes. So it's a big improvement. The accuracy is basically limited by the rasterization of boundary conditions in the finite difference solver, but it's essentially the same to perceptual levels. So if you're using it for visual applications or audio vision apps, you're probably not going to notice it. Here's some comparisons. They're basically identical. And yeah, I think I'll just end it there. And I think I'm actually finished 2 minutes earlier. So this is a first ever, I think.
Wow, yeah, it's first for this workshop. Well, thank you so much. Does anyone have questions for Doug? You can ask them over the chat and we'll read them off. Well, if not, I have a question. So you talked a lot about performing this simulation efficiently. I was curious how you did that for your inverse Foley work. How did you pare down that really big search space to figure out the visuals that could go with the audio?
Right, so the inverse Foley work, you know, we take the sound as input, right? And then so given the sound, we identify contact event times and amplitudes, periods of isolated impacts, and then also continuous events, which give us rolling and sliding kind of behaviors. And then from that, we basically use a database of rigid bodies that have been thrown on the ground in all kinds of different ways, and then looked at all of the contact event times between bounces that occurred and use those times to match up to the what we saw in the simulation, and then try to find ways. These are basically edges in a graph. Every simulation is just a sequence of events, of bounces, and then we would look for these time scales that matched and then find similar orientations and initial final velocities so that they were physically continuous and didn't violate equations of motions too much. And then we would do, you know, basically a graph search to synthesize simulations that also match the data. So there's no simulation at all. So it gave realistic sound because there was actually no sound synthesis, right? And so that was one of the goals, to see if we could go the other way too. But you could imagine using similar ideas. One of the examples we had in that paper was also just if you have you know, object that's tracked, you know, can you synthesize motion that matches the specific constraints on where the object should be and match the sound as well. So you can have other types of constraints, but the more constraints you add, then the worse it becomes. It's not like a but I think in general, like for vision, like Steve Seitz had a paper a long time ago on tracking rigid bodies. And they basically have some regularizer for smoothness of the trajectory to allow them to estimate it. But this discontinuities due to contact, the sounds tell you when you shouldn't be regularizing the motion, right? Because those are where all the discontinuities are. So you could try to estimate things using sound better that way.
Cool. Yeah, the simulations look really realistic. So if no one else has a question, I can ask another. It looks like most of the simulation is for rigid objects. You had some examples like slinkies that maybe deviate from that, or waves. What are the challenges in simulating non-rigid objects, like a stuffed animal or a cushion?
Right. Yeah. So we did some examples where we simulate things like cloth and stiff but still nonlinear shells, and fluids, fire, things like that. The problem with a lot of soft objects is they just don't make any sound. Like my cat, doesn't make any sound. And might meow or something. but they're just quiet. Like the cloth work that we did cloth sound synthesis. You can't do it from first principles because of all the unknown parameters and weird nonlinear vibrations and radiations. Are just basically sound like colored noise anyway. So we basically try to measure the friction properties and the crumpling properties and do some concatenative synthesis of that sort of thing. But the problem with those models is I just kind of really bugged me because they're not really as principled. Like you don't have these nice, elegant mathematical formalisms and fast algorithms. You're stuck in this kind of data-driven land, which, is okay and makes sense to do that for certain models, but it's nice to have a predictive out-of-the-box simulation where you say, this is what the model is, we simulate it from first principles. So that's one of the challenges, is that, again, like systems like, if you have a couch or something, like what are the material properties of that, So you do need to measure some things to nail it down, but in other cases when you can actually define things, it's much nicer. Yeah.
Cool. So you mentioned material properties. How do those change? I noticed a lot of these examples were with very rigid materials, like the simulated waves in glass. How do things change if if not the object itself, but the environment for more complex material in terms of material?
So the environment in terms of where the objects were interacting, or just the acoustics?
Or the way they would echo off of the...
Yeah, so there's like all of these interesting aspects of, so we're mostly modeling like sound sources, so we're not worried too much about absorption. We're trying to figure out what the source is, and then that can go in another simulation in general. Like it could be an architectural model or something. So there's all these kind of like, for long time scales, you have reverb effects of your room, which Zoom's a good demo of. But for a lot of close effects, you have a lot of really interesting near field effects where, if the bowl is going down or spolling, you get these cavity resonances or inter-object reflectances and things like that, which cause some shadowing. Another really interesting thing about, depending on the interactions and how you mic it, if you mic it really close, you'll also get evanescent waves, right? So like the whole ASMR thing is obsessed with, it's like all this community of people obsessed with evanescent waves, right? It's like what Walter Murch, who's this guy who did THX, the sound for that movie, calls the smell of the microphone, which is basically like the closer you put the mic to things, the more it'll distort the type of sound you hear. Just like, your earbuds, if you take your earbuds off and go across the room, the bass is really terrible. But if you put them in your ear, they're great, right? Because they just don't radiate effectively. And the same thing with an object, if you have like this thunderous roar of somebody tapping an Oreo cookie or something, it's because the mic is like jammed right into the object. But usually you don't like hear Oreo cookies that way. But you usually hear them through pseudo sound when they're crunching through your skull. But that's another pathway we usually don't listen to things through.
Great. Well, we're out of time now. Thank you so much.
Great. Thanks for having me.
Really, really awesome, inspirational stuff for us in the more of the computer vision side of things.
Thanks. I think this is a great workshop too, by the way. I think it's great to see things being considered together. Yeah.
Oh, thanks so much. Great.